Physics 2211 Lab 2 Sashwat Takal. This is the motion of a falling object lab. This lab has three main components. One, record an object drop from rest and falling straight down. Upload the recording to Tracker and find the object's position at corresponding times. Two, create a computational model to predict the first component but only include the force of gravity being applied on the object. Three, repeat component 2 but also include the drag force being applied on the object. The purpose of this lab is to compare the Tracker analysis and the computational models to see how similar/different the results are, to understand why these similarities and differences exist. Some background knowledge. Newton's second law. The final velocity equals the initial velocity plus the net force over mass multiplied by the change in time. Position update. The final position equals the initial position plus the average velocity times the change in time. Gravitational force. The gravitational force equals negative mass times the acceleration due to gravity, which on Earth is 9.8 meters per second squared. Drag force. The drag force equals the proportionality constant times the magnitude of velocity squared. Experiment overview. I dropped a mini basketball that weighs 0.011 kilograms. My mom recorded me dropping it. The system is the ball, the surroundings are everything else. Computational models overview. In both of my computational models, I had the same initial conditions for mass, initial velocity, position, and g. In the computational model that accounting for gravity and the drag force, the proportionality constant was 0.0038. In the computational model accounting only for gravity, the proportionality constant was 0. Brief overview of the results. The computational models that accounted for both gravity and the drag force had results that were much more consistent with the experiment in comparison to the computational model that only accounted for gravity. Experiment. In Tracker, I used the fourth quadrant of a Cartesian plane to track the ball's position at a given time. Since the ball was traveling downwards, I had the origin of the plane be the start position of the ball. The ball then started traveling downwards in the negative y direction. This resulted in a negative nonlinear slope. To get the location of the ball, I'll click on where the center of the mass of the ball was in each video frame. Here's a video. Computational models. In line 36, I set the ball's mass as 0.011 kilograms. In line 38, I set the original position vector as 000 meters. In line 39, I set the original velocity vector as 000 meters per second square. Just meters per second. In line 43, I set the starting time as 0 seconds. In line 49, I set the magnitude of the acceleration due to gravity as 9.8 meters per second squared. In line 52, I set the unit vector for the positive y-axis in order to make the other variables vectors. In line 56, I set the proportionality constant for the magnitude of the drag force. When accounting only for gravity, it should be 0. When accounting for both gravity and drag, it should be 0.0038. In line 65, I have a while loop to make sure the computational model only simulates the experiment for 0.633 seconds. In line 70, I calculate the force due to gravity. In line 71, I calculate the magnitude of the ball's velocity. In line 72, I calculate the drag force. This would be 0 when b equals 0. In line 73, I calculate the net force acting on the ball. In line 77, I update the ball's velocity using Newton's second law. In line 79, I update the ball's position using the position update formula. In line 82, I update the time. Results. The computational model that accounted for the drag force acting upon the ball was much more accurate than the computational model that did not account for the drag force acting upon the ball. Both of the models were pretty accurate at the beginning, but as time went on, the computational model that did not account for the drag force started to overpredict the position of the ball. This shows us that there is a force of drag acting upon the ball and that the drag force is acting in the opposite direction of the gravitational force. The possible errors, human errors using Tracker. Since I had to manually locate the center of the mass of the ball in Tracker, I may have been slightly off. This can affect the position of the ball. The proportionality constant for the magnitude of the drag force not being accurate. Because I had to calculate the proportionality constant for the magnitude of the drag force by running the code multiple times, then it might have not been completely accurate, which could affect the position of the ball. Additional questions. What does it mean? Examine the velocity versus time predicted by your models with and without drag. Which models, if any, predicted terminal velocity? Discuss briefly. The model accounting for both gravitational force and the drag force predicted terminal velocity. This is because as time increases, the magnitude of acceleration decreases in the model accounting for both the gravitational force and the drag force. In the model accounting for only the gravitational force, the magnitude of acceleration is constant. When terminal velocity is reached, the net force would be equal to 0. Imagine that the object was initially thrown downwards. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped just from rest? The terminal velocity would be the same. We can test this by setting the initial velocity in the computational model that accounts for both the gravitational force and drag force to be 0, -10 meters per second. Then we can compare the velocity versus time graphs that the model produces when the initial velocity is 0, 0, 0 meters per second and 0, -10 meters per second. The graph on top is the position versus time graph when the initial velocity is 0, -1, 0 meters per second. The graph on the bottom is the position versus time graph when the initial velocity is 0, 0, 0 meters per second. In both graphs, the final velocity reached is about the same. This leads me to believe that no matter if the object starts at rest or is thrown downwards, the terminal velocity would be the same. However, if the object is thrown downwards, it will reach terminal velocity faster. Conclusion. While both computational models showed similar results to the experiment at the beginning, the computational model that only accounted for the gravitational force tended to overpredict the position of the ball as the simulation went on. However, the computational model that accounted for the gravitational force and the drag force was much more accurate with the actual experiment. This shows us that the drag force is present in the experiment and is acting on the ball in the opposite direction of the gravitational force.